So recently we have been looking at the topic electric field, electric forces, you name it. And so I would have sought to look at various past paper questions surrounding the concept of electric field, more predominantly when we have a parallel plate, uh, you know, scenario type of questions. All right. So to begin, the question starts, and this is our OCR 2011, I believe, past paper question. So you can check it out as well to confirm whether the working notes is indeed correct. So first thing first, they ask us to define the electric field strength. Now, by nature, once there is a charge, there will be an electric field. That electric field is dependent on, obviously, the force of interaction that takes place between various charges. And so, pretty much, your electric field strength is nothing more than the force that is experienced per unit charge. So that's how we pretty much defined your electric field strength. So uh, a charge is placed at some distance from another charge. That charge will have some type of force acting on it. And so for that reason, we say that the electric field strength is the amount of force that the test charge will experience per unit charge. Yeah. All right. Now the question continues, and it says that figure 3.1 shows two parallel plates, metal plate A and B, and each of them has their own potential difference. So we can see that plate B has a positive 3.4 kilovolts, whereas the top plate has zero potential. So this obviously would have created a potential difference of 3.4 kilovolts. Now it says that based on this arrangement, it provides a uniform electric field. Now your task is to draw at least 6 lines to represent the electric field between the plates. Of course, that is quite simple to do. Now what you need to do is to look at which plate is more than likely the positive plate. All right. So plate B would seem to be the positive plate because it has a positive potential, and so I would expect that my E fields would be moving from the positive plate to the, so in a sense it will be moving from plate B to plate A. All right, so this is how your field lines should look. Of course, they say at least 6. Now your field lines runs generally from the positive plate to the negative plate. So this is what we're expecting to do. Obviously, you can put in the rest of the, it says at least 6. So, I mean, it doesn't have to be exactly 6, but at least 6. Right? And in essence, you can see that when you have a parallel plate scenario or two parallel plates, that is telling us that our electric field strength will be a constant value wherever you are in between the plates. All right, so that's where you'd have gotten your 2 marks from. Now question C goes to another dimension. It gives us some information here. Of course, tells us that the plates are separated with a distance of 0.05. The distance that the electron traveled horizontally is 0.04 meters, right? So that's pretty much how long the plate is. The electron is traveling at a horizontal speed of 4 times 10 to the 7 meters per second. And I think that's what we need to know so far. I think there might have been a typo with the question here, but if you look at this, this is what you would use instead of the centimeters. All right, so just pay attention to that. Now they want us to draw an arrow on figure 3.2 to show the direction of the acceleration on the electron at point P. Now, as you can imagine, we would have established that this is how the E field would look for the parallel plate arrangement. Now, if an electron is fired in between the two plates, by nature we know that negative and positive attracts. So we would expect that our negative electron will tend to create a type of projectile, deviating towards or bending towards the positive plate. Now we're concerned about what's happening at point P. Now at point P, right, I would expect that my acceleration would be directly downwards. So just from a pictorial standpoint, so we're just zooming in at that very instant as to what will happen to the electron. Imagine that if the electron was supposed to stop at that point, where would it accelerate? It would definitely accelerate downwards. So that pretty much captures that 1 mark question. So imagine that we want to figure out the acceleration that the electron has between the plates. Yeah, they gave us the value, which means that it's just a simple proof. Now, the thing that we're going to start off by trying to establish is that seeing that the electron is accelerating under the influence of the electric force, then we should be able to again see that Newton's second law would obviously be applicable in this case. So, force is equal to mass times acceleration. Now, as you can imagine, the force that is causing the acceleration is the electric force, and that by definition or by formula is going to be E, which is the electric field strength, times the charge. Now let's just quickly transpose the equation to make A become the subject. So acceleration is nothing more than the E field times the charge divided by the mass of the electron. As for the E field, we know, seeing that it's a parallel plate scenario, the E field is going to be the voltage or the potential difference divided by the distance of separation. Of course, you can work out that. When you work that out, you should get a value that E is, so when we work out E is going to be 6.8 times 10 to the 4 volts per meter. Take that value, we're going to put it here. So we have 6.8 times 10 to the 4 times the charge of an electron, 1.6 times 10 to the minus 19. It's also divided by the mass of an electron, which is 9.11 times 10 to the minus 31. Having done all of that, it should have proven to us that our acceleration is going to be pretty much 1.19 times 10 to the power of 16 meters per second squared. So that encapsulates that. Now, I like these type of questions sometimes because if you didn't know how to find the answer for the acceleration, you already know the answer, so it wouldn't stop you from working out the other parts of the question. Now, as per the part 3 of the question, it says calculate the time taken for the electron for an electron on entering the plate to reach point P. So let's look back at the diagram. Right, so here we have our electron entering. One of the things that the question highlighted to us is that point P is 0.04 meters from where the electron enters. So from this point to here, that distance traveled is 0.04 meters. So that will be considered as the horizontal distance. Now, if you look at the electron is fired horizontally at the start. So we can use the concept of projectile motion, and that along the horizontal there's only one equation that we can use along the horizontal, and that is pretty much v is equal to, or speed is equal to distance over time. Now we know what the speed is based on the question. We're now trying to find the time, so time is going to equal to distance over the speed, or the velocity if you want to consider it to be that. So in this case, distance, as you know, is 0.04. The velocity is given to us in the question as 4.0 times 10 to the power of 7. Once we do all of that, we know what the time now is when the electron is at point P. So that's 1 times 10 to the power of minus 9 seconds, or we could say 1 nanoseconds. All right. So I mean, of course, that's a very short time, which means that the electron is moving obviously at a very high speed. All right. So with that being said, now it says that we should show that the vertical velocity of the electron at point P is 1.2 times 10 to the 7 meters per second. So clearly we're concerned about what's happening at point P again, and this is now taking into account vertical motions. All right. So of course, you know, we're looking at SUVAT equations, right? I mean, there are several that we could possibly use to figure this out. In terms of, we don't know what S is. Let me check if we know what S is. So for sure, let's just talk about the velocity. We know that because the object was launched horizontally, right? Then the initial vertical velocity, that's going to equal to 0. Sorry, the initial vertical velocity, so u is equal to 0. We're trying to find v. We know what the acceleration is based on the question above, 1 times 10 to the power of 16. All right, and at least we know what the time is at that point. To be honest, time is an independent variable, so that won't change. So that 1 times 10 to the power of minus 9 seconds. So we have a bit of information that we know. It's just for us now to see which equation is most applicable to finding out the rest of the question. As regards to where the object is positioned, let's look back at the question if there's any information as to how far point P is. I don't think we know what the height is for point P per se. It didn't tell us that, so we have to think carefully now. So let's think about the equations that we could possibly use. Show that the vertical velocity. Alright. So I would suggest that we use v is equal to u plus at. Our acceleration, when we had calculated our acceleration gave us 1.2 times 10 to the 16. If we multiply that up together, we will end up getting 1 second here. Right, we get 12 million, which we can obviously rewrite that as 1.2 times 10 to the power of 7 meters per second. So that is basically what the speed, the vertical velocity is when the object is at point P. So as you can imagine, we didn't know the distance, right? So we couldn't have used any other equation of SUVAT to solve the question. It says calculate the magnitude of the resultant force at point P. So for us to do that at point P, right, you know, we have the horizontal velocity and we have the vertical velocity, which is going downwards. So it is for us to literally find the hypotenuse of that, which is us using Pythagoras theorem. So as you can imagine, Pythag would say that a squared plus b squared is equal to c squared. So c, which is the hypotenuse, will be equal to the square root of v of x squared plus v of y squared. So if we check back what the horizontal velocity was, horizontal velocity was 4 times 10 to the 7th. So we're going to square all of that plus the velocity vertically, which we worked out to be 1.2 times 10 to the 7th squared. Once you have done all of that and found the square root, then you would have seen where the net resultant velocity is, so VR is actually 4.1 times 10 to the 7th meters per second. All right. Now, as for the kinetic energy, we would literally use the equation that says Ke is equal to a half mv squared. Seeing that we want to find the kinetic energy not just along the horizontal or the vertical, we have to use the resultant velocity to find that. So a half times your mass of the electron times v squared, where v squared in this case is going to be 4.1 times 10 to the 7. All of that is being squared. So once we work that out, we should get a value to say that our kinetic energy is 8 times 10 to the minus 16 joules. And that would encapsulate the different working notes surrounding this question. So as you can imagine, the question somewhat encapsulate various aspects of your physics knowledge, so to speak. So it's important that we can recall every aspect and put it together in a cohesive way. All right, that's it for now.